Greetings. In this video, I'm going to talk about the very important issues of stress and strain, as well as ductility and elasticity. So we'll talk about the concept of pressure, as well as I said, stress and strain. They go hand in hand. Some different types of stresses. We'll talk about the stress-strain curve, as well as, again, ductility and elasticity. So one could say that the structural engineer's big goal is to make sure that our structures have enough strength to withstand the external forces that will be applied to them during their lifetimes. Therefore, engineers need to predict and measure the effects of those forces. And this presentation will look at the stress and the strain that occur in a structure when those external forces are applied, and how the structural engineer can achieve structural safety while limiting these stresses, by limiting these stresses. Okay, so pressure, all right, describes when a force is distributed over part of an external surface of a structure as opposed to being applied to a single concentrated point. So we're going to talk about a lot of kind of geometric and relationships and what happens when forces are applied to buildings and how they move throughout buildings. So a lot of it's important terminology to describe exactly where things are occurring. So pressure is occurring over a surface, over an external surface. It talks about forces that happen at the interface between two materials. So water on a floor or a roof here, so that pressure is occurring right where the water meets the roof. Window on the wall of a building. So this is a common diagram for wind loading on a tall building, or any building for that matter. And so here's the wind pressure coming on yellow, and right where that yellow wind meets the face, the glass, or the wall, that's exactly where the pressure is occurring. Sand or anything, really any weight meeting a floor. So pressure could be described as uniform or non-uniform. Okay, so this pressure is non-uniform, and on this side, the leeward pressure, that is uniform. That's what the length of those yellow arrows indicate. So here, the pressure is greater at the top of a building than it is at the bottom. On this side, we have uniform pressure. Okay, stress. So external forces, loads, create internal forces. We've discussed this. Compression, tension, that's happening internally. Stress describes the magnitude of those internal forces. Okay, so it's describing something that's happening within a structural member. Similar to pressure, which we just discussed, stress is typically not concentrated at a single point, but usually distributed over some internal area. All right, very important. So we're not talking about single points. So again, wherever this water is meeting that roof, that is the location of the pressure. And stress is happening inside of a structural member, described in relationship to the member's cross section. All right, so here is a glue laminated timber, and we've cut it in half, and we see its section. So the stress will be discussed in terms of this area, in the geometry of this area, the area, the square inches or the square feet that this area takes up, basically. Same with this. Here is the cross-section of an I-beam. And if you go into the steel manual, it will tell you exactly what the cross-sectional area is. And this is very important to engineers because this is how they discuss stress, which is a super important concept when it comes to designing structural systems. Okay, so stress, the total internal force divided by the internal area over which the force acts. So it is in the denominator of this equation, the area. All right, so pressure is on a surface and stress is within a material. Very important distinction. Both care about areas. Okay, two types of stress. So this is just a bit more basic vocabulary and discussing geometric relationships. So we have internal stresses that are normal forces or shear forces. So here A would be normal, and that is a perpendicular reaction or relationship there. And B, it would be a shear stress. So this bolt or whatever it is that's been fastened to this wall, it has a perpendicular relationship with the wall, and then it has a shear stress that's being occurred because the wall is pushing up and this thing is pushing down, and there's a shear that's happening between them. And that's what we see here. These are perpendicular relationships, normal relationships, normal or perpendicular, and then shear is parallel. So this is the only parallel one that we see. Otherwise, this whole group here is describing normal reactions. Okay. All right. So normal stresses tend to make objects become longer or shorter. So that's what we see here. We saw that in a previous lecture. We discussed tensile and compressive stresses or forces. So here we have something being crushed. Here we have something being pulled apart. And then we have shear, the relationship. So objects sliding over other parts, the relationship between our hand and the rope pulling on it. That makes sense. Or two fingers rubbing against each other right there. The shear is happening right at the interface of those two parts of the material, parts of the object, or different objects for that matter. Okay, so stress is the amount of force for a given unit area. Okay, stress is the amount of force for a given unit area. So that is a amount of force described in relationship to that cross section. Okay. Strain is defined as the unit deformation or movement per unit of original length. Okay, so this is the stress-strain curve. This is a simple version of it, and here's the stress on the vertical axis, and then here is strain on the horizontal axis. And what this is going to tell us is as the stress is increasing, what is happening to the strain. So we're going to chart the relationship between these. So we could see that this line here is telling us as the stress is increasing, something is happening. The amount of strain is growing, and then it kind of tapers off, and then it fractures. So the relationship between the stress and the strain is what's being charted here. Okay, so that's the amount of force that's occurring inside the object, and strain is the amount of change or deformation that's happening to that object. Okay, it's deforming. As the stress is increasing, some object is deforming. And deformation of the material is the change in geometry when the stress is applied. So we talked about Newton's law, and we said that things are either going to accelerate or slow down. That's in basic physics when we're talking about a ball that's rolling or something. We care more about buildings, and therefore the geometry changes. We don't typically have things that are accelerating or slowing down. We have beams that are having their geometry changed. So as the stress is increasing in that beam, the beam is deforming. The geometry, the actual beam is deforming. That strain is occurring as the beam is deforming. And that's what's being charted here, okay? Elastic or plastic deformation, two different ways that things deform. So elastic is reversible. So if we think about the elastic band, once the forces are no longer applied, the object returns to its normal shape. So we pull on a rubber band, it stretches, we let go, and it snaps back. That happens with beams as well. Anything. I'm just talking about beams, but they're columns, arches, everything. It refers to all structural members and systems. We could talk about a specific structural member, a beam or a column, or we could talk about the system, the entire house, which is made up of many. So this concept applies to both. So, and then we have plastic deformation, so not irreversible. So we stretch something and then the load goes away, but this thing has been damaged, and this type of deformation, it's been stretched out and it's never going to come back. Okay, so some basic definitions there. All right, so now taking a closer look into the stress-strain curve. So the yield strength that's occurring right there. So this is the blue elastic region, and then right here we have a change in color, and it goes into the green plastic region. So elastic, things snap back. Plastic is permanent deformation. So this point is the change between plastic, elastic, where things are snapping back and everything's okay. And then right here, some permanent damage has occurred. And now when that load is taken off, it's not going to bounce back to the way it was. Some permanent damage has occurred. So the point on the engineering stress strain curve beyond which material begins to deform and cannot be reversed upon removal of the loading. So right there, permanent damage. The lowest stress that gives permanent deformation. Yes, that's what that is. That describes it as well. The point between these two regions. Yes, so that's three different ways to describe what yield strength is. The point at which permanent damage occurs. All right, and then we have the ultimate strength. So the point on the engineering stress strain curve corresponding to the maximum stress an object could withstand. So this is not pointing to fracture. Okay, this is pointing to, what it's really pointing to is the highest point on the stress strain curve. And I'm saying that, pointing that out clearly as being, because this diagram is a little simple. Sometimes we'll see these, they'll come up and then they'll come down. They'll meet their maximum stress, and then they'll actually, the stress will actually reduce, and then it'll kind of plateau and fracture. So it's really whatever point is the highest on this Y stress axis. All right, so we're coming straight across. So if there's a little peak, it would be the peak. Okay? All right, so the maximum amount of stress that was taken is right there. Okay. In many materials, the relationship between the stress and the resulting strain is directly proportional up to a limit. And the graph representing these two qualities is a straight line. So that's right here. That's the elastic region. So a perfectly straight line means that the relationship between the stress and the strain is proportional. So if I add 2 units of stress, I get 2 units of strain. And this is like a 45-degree angle. So, and again, this is just a simple example. We'll see very soon, we'll see lines that run on sharp angles. We'll see lines that sit on flat angles. This is on a 45, so that's why I'm throwing out these simple numbers. 4 units of stress, 4 units of strain. 6 units, 6 units. And that's mapping what exactly happens. And what this is saying is that relationship between that stress and that strain is proportional up to a limit. And that's why we get a straight line. If it was not proportional, it wouldn't be straight. If it was 6 and 2, and then 10 and 5, and it was jumping all over, this line would not be straight. All right, the slope of this line is a measure of the stiffness of an elastic material. Stiffness. So as we dig into the world of structures, we're going to see a lot of different words that describe different types of strengths. And in common language, they're often used interchangeably. Something strong, something stiff. But there's a lot of different types of strength, and we're going to have to be very specific. And stiffness is a very specific, very important quality, and it's coming right off of this line here. It's the slope of that line. We'll dig more into that. It's known as Young's modulus, or the modulus of elasticity, or the tensile modulus. These are 3 things that are the same, and you should know this name. It is the measure of a material's stiffness. All right, and this stress strain curve, just to back up a little bit, is going to be charted for all different materials. Concrete has one, all different types of wood, so oak has one, cedar has one, all different types of steel have a stress strain curve. So all different materials have their own stress strain curves. And what this is, one thing that the stress strain curve is going to tell the engineer is what's Young's modulus. How stiff is this material? So there's a lot of components and different ways for engineers to describe things. But one of them, one basic kind of benchmark is Young's modulus. And it's basically saying from one engineer to the other, how stiff is that piece of steel? And the answer is, it's very stiff, due to Young's modulus. Okay, so it's a basic important piece of information that comes off of the stress strain curve. Okay, so So this is defined as the ratio, so the modulus. So again, just to go back one more time though, in the elastic region, that's also very important, is that this only pertains, this measure of stiffness, this modulus of elasticity, is only pulled from this elastic region here. Once we go into the plastic region, this is no longer part of the discussion, all right? Okay. So it's the relationship of the stress over strain. It's created during tensile stresses. I'm going to show a quick video of that. Modulus is calculated. So it's calculated by defining the stress over the strain. So it's actually put into a formula, and that's how we get to that piece right there, the elastic region.
500 diameter tensile specimen, stainless steel material.
Okay, so this is a tensile test that's occurring inside of a laboratory. So this is what structural engineers would study in universities. They'd have this type of equipment. So this is the bar right here, this piece, and they are attaching these sensors to it, and they are weighting it. So it is in a hydraulic press. So this piece and this piece have been connected to it, and it is pulling. It is pulling this pulling it apart basically. So we know tension is a pulling in two directions. So this piece is being pulled, and however this bar is reacting, it's all being plotted.
After yield strength has been determined, remove extensometer and continue test to failure.
Okay, so they just said that the yield strength has been established. So now permanent damage has occurred, and we could see this thing getting thinner and thinner right here. And all that's being charted right there. We could see it. So now it's starting to fracture, and this is all being charted on the stress strain curve. And fracture. Okay, so that's what it really looks like. So that was all charted right along there. I wish they had shown us that part a little better in the video. But he described exactly when that the yield point was reached. So that's when the permanent damage occurred. And then you could see in that plastic region, all that damage beyond that point was just permanent. There was no way that structural member, whatever it was, would ever return to normal. It was permanently damaged. Okay, let's look. This is a good one here. So this is, again, very, very simplified. And what this is showing is 4 different materials, A, B, C, and D, and how they react as they are loaded. All right. So A is the strongest and the stiffest. Okay. So it is the stiffest because it has the steepest slope. All right. So let's just go back one more time here. Okay. So the slope of this line is a measure of the stiffness. All right, and that again, that's the ratio of the stress and the strain, and this is right in the middle. So 2 units of stress gives us 2 units of strain. Imagine if it was 4 units of stress and 2 units of strain. That would be a sharper, a greater angle. 4 and 2, 8 and 4. And that would produce a linear relationship that ran like this. And what that would be showing us is that if it was doing 4 and 2 rather than 4 and 4, that means that this steeper line is a stiffer material because it's taking more stress with little strain. More stress, more stress, little strain. Or the opposite could be a little bit of stress and a lot of strain. A little bit of stress and a lot of strain. All right, so this blue one is right in the middle, and that's a 45-degree angle. So it's kind of like 4 and 4. 4 units of stress, 4 strain. So steeper is stiffer, less steep, less stiff. Okay, so A is very stiff, B, less stiff, C, less stiff yet, and D, the least stiff. And that only applies to that point, that yield point. So once this thing starts arcing or doing whatever it's going to do, this one just vanished. So at that point, it doesn't matter. At this point, not that it doesn't matter. It's no longer a question of stiffness. At this point, it's no longer a question of stiffness. This is the stiffness, okay? So A is the stiffness. A is also the strongest because it reaches the highest up here. It could endure the most amount of stress. It comes all the way up to this point, and this is what I was talking about a few slides back. So right here, so what is the strongest material at its strongest point? The answer is right here, okay? It's not down here. When it's down here, it's actually taking on less stress. A reached its max strength right here. C reached its max strength right here. And then it declined. B just reached its max strength and fractured right there. It didn't have any afterlife and permanent damage. All right, so let's go on to B. B is the most brittle because it fractures suddenly. So we'll talk about that next. Elasticity and brittleness. So there was no permanent damage. This thing just broke and shattered. And shattered's a good word because it's like glass. Some things could bend and show us that they're about to break. Other things just shatter. C is the most ductile because it extends or stretches the most. So this one is creeping up, creeping up, creeping up. Permanent damage occurred, but it really lasted a long time after that permanent damage occurred, which is how we like buildings. We like things to creak and bend and give us warning so we get out of the building, basically. This doesn't give us any warning. This thing just shattered. Everything appeared to be fine, and then it just broke. D breaks before C with a lower stress. So it's least stiff, and then it has some afterlife, but then it does break. So it's not very strong at all. It is pretty ductile, but it's not very strong at all relative to the other materials. Okay, so brittle material. So here, another version. So here is brittle. So right here, so it has a high yield strength, and it's stiff because it has a great slope, a very steep slope, but it has a short afterlife. It's just brittle and it breaks. Ductile, however, so this is not as stiff as whatever this is. We don't know what these materials are. These are just examples. So this is less stiff. It also has less strength because it does not climb up the stress axis nearly as much as this one. But this one is far more ductile. So less stiff, but more ductile. And that's often the case. Not always, but so this one has permanent damage, but it lives for a long time thereafter. This is a brittle failure for wood, right? Typically, wood is considered pretty brittle. It just breaks. It doesn't stretch too much. So brittle materials, little tendency to deform before fracture. So not a lot of deformation. This bent some, but it did not deform much. It just broke. The fracture absorbs relatively little energy, even in materials of high strength, and usually makes a snapping sound. So absorbing energy, that's very important. So the longer a material lives, the more energy it could absorb in terms of stress. Okay. Brittle materials give less warning than ductile ones as they approach failure. So this is a dangerous situation that we don't like in buildings. All right, elastic materials are the ones that bounce back. We talked about that. Brittle ones like ceramics or glass do not experience plastic deformation and fracture quickly. Okay, so they do not experience that plastic deformation. They don't experience this part of the curve. All right. Materials such as metals usually experience low amount of plastic deformation before failure, while softer ductile polymers will plastically deform much more. So rubber bands, I think I was thinking about rubber tires. Rubber tires, they take a real beating. They might not be the strongest material, but they are very, very ductile, and so they kind of have an endurance. They don't just snap and break typically. Sometimes they blow out, but they could also take a lot of damage before finally going under certain circumstances. Okay, masonry construction systems. So we could talk about, and we will talk about, structural members, just columns or beams, but we could also talk about entire systems. So this is a masonry system and this is a wood system. So masonry construction systems are brittle, so very brittle. So they, unfortunately, and they're because of limited resources in certain parts of the world, masonry systems are used where there's not a lot of wood and also where it's hurricane prone, unfortunately. So that's a bad combination, masonry plus hurricane prone, not hurricane, earthquake prone areas. Very dangerous combination, unfortunately. So masonry as a system is very brittle. It's very brittle. It breaks very quickly without, or not quickly, but it doesn't give warning. It doesn't give warning. So it breaks suddenly. Not quickly necessarily. Wood, however, while typically brittle by itself, when it's put together in a system, is actually quite ductile. So residential kind of low-rise platform building is actually quite ductile, and in the case of a earthquake is one of the preferred systems to be in. So this building will never be the same again. Obviously, it'll have to come down. You can never repair that, but it's survivable. It's survivable. You know, you get a lot more warning in a situation like this than you would here. Okay. All right. Two more slides and just a little bit of math to explain this here. So stress is the amount of force per. Actually, I think I'm just going to pick this up and move this over to another application. Okay, I just wanted to change applications and get out of PowerPoint so that I could actually draw this. Let me just get a marker. Okay, so stress is the amount of force for a given unit of area. Okay, so we talked about that. That is going back to the cross-section. The cross-section, defined the cross-section, is typically measured pounds per square inch. So example, 1,000-pound load was applied to the edge of a block of wood measuring 2 by 2 inches in cross-section by 10 inches in length, and the applied strength would be 1,000 pounds divided by 4 inches. Okay, so 1,000-pound load, not the easiest to draw with a mouse, applied on the edge of a block of wood measuring 2 by 2 inches, 2 by 2, 10 inches in length. The applied stress would be the 1,000 pounds divided by the 4 inches. So this section right here this is the cross section, and that is the 4 square inches. And we take that 1,000 pounds, divide it by the 4, and we get the 250 pounds per square inch. So it's describing that per square inch is describing this area right there. Okay? And that is stress divided by force equals area. So you will notice that that 10 did not come into play yet. Okay, now I'm jumping into the final slide. So when external forces produce stress, the body often undergoes a change in shape or dimension. So we just discussed the stress, that 1,000 pound that's being loaded on the edge of that block, and something's going to happen. So strain is what occurs. So the change in dimension expressed as a ratio of the original unstressed dimension. All right, so we have the stress that's being applied, and what results is change, which is strain. Okay, so and that change in length divided by the original. Okay, so we have our 10-inch long block, and it is compressed by 0.002 inches. Okay, so I'm just going to jump back and draw that 0.00. Okay, so again we have our block of wood, 2 by 2, 1,000 pounds. 1,000 pounds coming down, This was our 2x2. Now we've established the amount of stress, the 250 pounds per square inch. That was established with the 2x2. Now we don't care about that. Now we care about the 10 inches that has now suddenly been crushed. So right here we lost 0.002 inches. So we had a crushing of that. So then the strain, therefore, is that change by the original. So that change by the original gives us a strain of, so it increased from 0.002 inches, and then we divided it by the 10. So now we are at 0.0002 inches of an inch, and that is the amount of strain. Okay. All right, so that sums up that this lesson there. So we talked about pressure, we talked about stress and strain, we spent a lot of time on that curve, and then the ductility and the elasticity. Okay, thank you very much.